All right, acceleration due to gravity. We remember this from grade 11 physics, acceleration due to gravity, sometimes written as just A for acceleration due to gravity. Sometimes you'll see a little g, sometimes just little g. Anyways, all acceleration due to gravity, all 9.8 meters per second down. That's on Earth, meters per second squared, I should say. Down, that's on Earth. If you were to go to the moon, it's a different value, 1.6, I think. Mars is 3.6 or something. But everywhere where we are on the surface of the Earth, it's 9.8 meters per second squared. I wanted to talk quickly about what those units mean. Let's just make the math easy. Let's say, let's choose a different number altogether. Let's say if acceleration was 5 meters per second squared, what does that mean? Here's what it means. If I did a little time and speed or velocity chart, let's say at time 0, I'm going 0 meters per second, time in seconds. After 1 second, how fast am I going? Well, if I'm going 5 meters, if my acceleration is 5 meters per second squared, I will then be going, after 1 second, 5 meters per second. After 2 seconds, I'll be up to 10. After 3 seconds, I'll be up to 15. What this unit is saying is, for every 1 second that passes, my speed increases by 5 meters per second. So you can say I'm adding 5 meters per second per second. Okay, so for every 1 second that goes by. The next second that goes by, I add another 5 meters per second per second. Okay, so I'm adding 5 meters per second for every 1 second of time that goes by. Okay, so I'm adding 5 meters per second. Again, how long did it take? It took a second per second. Okay, so 5 meters per second, what that means really is, if you kind of think of your fractions, meters per second, let's forget the 5 for just a second here. If I said meters per second, that's like seconds over 1. Okay, let's make this line big. Meters per second per seconds over 1. If I divide fractions, that's the same as multiplying their reciprocals. So the 1 over seconds, seconds over 1 becomes 1 over seconds. If I multiply this out, I'm going to get, I'm kind of off the page here, but I'm going to get meters on top. Meters times 1 is meters. Seconds times seconds is seconds squared. There's your unit. Meters per second squared means meters per second. How does your meters per second change per every 1 second of time that goes by? Okay, so that's what the unit means. Do heavy objects fall faster than light objects, is what I mean by that statement or that question. No, they don't. In class, I would drop 2 objects. You can try dropping a heavy object and a light object and see how they fall. You might ask about, like, what if I drop a feather compared with a hammer or something like that? You know, the feather's going to kind of float down and the hammer's just going to fall straight down. And that's because of air resistance. If we can ignore air resistance, then all objects fall at the same rate. If we have to include air resistance, then some objects are affected more. That does have to do possibly with their mass, but also with their surface area, very much so their surface area. Okay. Talking about that surface area, I guess, terminal velocity, somewhere that we experience that big surface area is with a parachute. So I don't know, I'm not a very good drawer here, but you can imagine here's a person, they're falling, and then here's their giant parachute. Maybe their ropes are going out like this. The reason a parachute is so big, it has to have a lot of surface area. You can imagine as the person is falling, there's all these like air molecules. Imagine dots all around here, right? Air molecules. The person doesn't kind of run into very many air molecules, but this giant parachute runs into a lot of those air molecules. It's a little bit like if I was moving my hand like this and there was a bunch of marbles on the page. You can kind of imagine I'm sort of scooping up marbles. This parachute is kind of scooping up those air molecules as it goes. Because it runs into so many, it slows objects down. So you could run into some and you're gonna slow down because of air resistance a little bit, but a big parachute is gonna slow down a lot because of air resistance. Okay, so if I kind of run through this, an object falling to the earth with only gravity acting on it experiences what we call free fall. Free fall means only gravity acts. So if I was to draw you a free body diagram of this, an object falling to the earth with only gravity acting on it, this is free fall. Okay, so kind of think back to our free body diagrams. A skydiver, so let's assume that that they've put their well, let's even forget the parachute. Let's just say that they are skydiving. So the person is kind of skydiving in the spread eagle position as they fall down this way. As they jump out of an airplane, they're going to experience free fall momentarily because they're not going very fast. But as they speed up, okay, so air resistance increases as the diver's speed increases. So as you start going faster and faster, you're running into air molecules at a quicker and quicker rate. Okay, so as speed increases, this force of gravity does not change. Fg is the same, but you start to get air resistance, so F air. Air resistance starts to increase a little bit. And as you keep increasing your speed, again, gravity doesn't change, but air resistance starts to change. It starts to get bigger and bigger. You kind of know this instinctively, right? If you're driving down the road in your car and you roll your window down and you stick your hand out the window, if you're not going very fast, there's not much air resistance. But as you go faster and faster, like if you're driving on the 401, 100 kilometers per hour, you put your hand out the window, you really feel that air resistance. And that's what's going on here. The faster they go, the bigger this air resistance gets. And eventually, air resistance gets so big that it is equal to gravity. When that happens, acceleration becomes zero, your speed becomes constant. That speed or velocity is what we call terminal velocity. What it means is your speed is no longer increasing. So here, V is still increasing. There's still an acceleration. Here, V still increasing. Not as much acceleration, but there's still acceleration. Whereas here in this last case, let's maybe stick a box around it. Here in this last case, when the forces are balanced, acceleration becomes zero, velocity or speed becomes constant, and that is terminal velocity.